Next, we move for connectivity and the types of joints. Right. Now, connectivity is very simple. It just means that suppose you have the two links, right? And suppose this one is the fixed link or the input link, and this is the output link, or this is the fixed link and this is the output link. So motion has to be transferred from here to here or from input to output. So we need to connect these two, right? So to connect these two, we need a joint, right? As we saw in the first slide that two links were connected by some joint. So we need a joint here in between these two links. So if that joint is connecting one of the link, then it will be, this link will be the fixed link and there is a joint, and this joint here is connecting one of this link, then it will be having the connectivity as 1. And if this joint here is able to connect one link here and there may be one more link here, then this will be connectivity 2. Is that clear? So the base link will be there or the input link will be there, but how much other links that the joint can connect will give you the connectivity, right? So this is about the connectivity. Degree of freedom we'll just discuss. So this is the first type of joint, which is known as the linear joint or the prismatic joint. These are also called sliding joint. So you can see that this is one of the links. This is the input link, right? And this is the output link. And this is the joint. So this joint, yes, this angle is fixed. So this cannot rotate here, but this can only slide up and down. So that's why this is known as the sliding joint or the prismatic joint. So the motion of this joint is only in one direction. That's why we say that degree of freedom is 1. We'll talk about degree of freedom a little bit later. So we say that degree of freedom is 1. So this joint will be the prismatic joint, which will be actually sliding up and down only. So it will have only one type of motion. Next we have revolute joint. So this revolute joint is basically, you can see it is cylindrical in nature. This distance is fixed here, right? In the previous case, this angle was fixed and the distance was variable. But here the distance is fixed and the angle is variable. So this can twist around this axis. So this is the axis, right? This vertical axis. About this vertical axis, this output link can change this angle. So this can move or this can rotate about this axis, right? So this is the revolute joint. Now revolute joint is basically a part of rotary joint, right? The rotary joints are basically two types. One is revolute and one is twisting. Rotary joints are basically revolute and twisting. So twisting, and what is the difference basically? So you can see this is the output link, right? This is the axis of the output link, and this is the axis about which the rotation is taking. So if these two are perpendicular, then it will be revolute. But suppose you have something like this. This is the axis and this joint is actually moving about this axis only. Suppose there is a link here. So the output link is rotating about the axis of the output link, and the axis of rotation are same. Then this will be twisting. This is represented by T and this is represented by R. So a little bit difference is there, but more or less now we use this word only, revolute word, right? But I just wanted to tell you what is the difference. So the difference is of this angle. If they are same, if both the axes are same, then it will be twisting, and if the axes are perpendicular, then it will be revolute joint. So again the degree of freedom will be 1, because this can only have movement in one direction. This can only rotate about this axis. So this degree of freedom is 1. But in case of cylindrical joint, we have degree of freedom as 2. Why? Because now this distance is also variable. So this cylindrical portion can move up and down, and also this can rotate about this axis. So it will be having 2 degree of freedom. It can have two motions, up and down motion and this rotation about this z-axis. This is the hook joint. So again you can see, and this can be the input link and this is the output link, and you have this two joints connected perpendicular to each other. So this will be moving in this direction, rotating in this direction, and this will be rotating in this direction. This will be having left right movement, this will be having top down movement, right? So this will be having 2 degrees of freedom. It will be having two motions in perpendicular direction, right? One of the axis will be this and another axis will be this. So this will be having again 2 degrees of freedom. This is generally not used in industrial robot or manipulator or serial robot. This is actually used in the parallel robot. We'll talk about serial and parallel robot again. So this is used generally in the parallel robot, not in the serial robot. Next, again we have this ball and socket joint or the spherical joint. This you might have seen, you might be playing the video games, so you might have used the joystick, or in modern day cars you have this side glass. That side glass also has one stick, and if you move the stick, the glass is adjusted. So it is similar to the joystick, and it will be having degree of freedom as 3. So it can rotate in 3 directions. So suppose this is X direction, this is the this ball, this socket, this is the socket, this is the link. So this is the input link and this is the output link, the ball and this rod or this stick. This is the output link. So this is the x-axis, this is the y-axis, and this is the z-axis. So you can move it in any of the directions. So these directions are shown here. Suppose you have 2 coordinate frames are shown here. You can see the coordinate frames. One is x, y, z, and another is x1, y1, and z1. So one of the coordinate frame x, y, or x1, y1, z1 is movable. That is this stick wala part, right? So x1, y1, z1, first it will be rotated about the z-axis. So after rotation it will look like this. After rotation this y-axis will move from here to here and this x-axis is moved from here to here. Next you can have the rotation about this x-axis. So after the rotation about this x-axis, z and y will be moving. So y will be moving here and z will be moving here. X will be stationary here. Next we can have movement about y-axis. So if this y it is moving about the y-axis, then x, y, z this will be moving. So this will be the final orientation with respect to the base frame x, y, z. So we'll be dealing with all these things. I'll show you the animations and all. And there is one software which is known as Robo Analyzer. We'll be doing all these things in the Robo Analyzer also. So important thing is that we have 3 degrees of freedom in the spherical joint. Again, this is not used in the serial robots or the manipulators. They are basically used in the parallel robots. So in industrial robots or the manipulators, we generally use 2 types of joint, the prismatic one and the revolute joint, right? So this is all about the joints. Then this is the representation of the joint. A revolute joint is represented by this circle, right? And this is the representation of the revolute joint, or this is another type of representation of revolute joint, which generally we represent it by like this. Then this is the representation of the prismatic joint, and this is the cylindrical joint, right? These arrows are also important, right? And this is the spherical joint, this is the hook joint, there are 2 axes this is the twisting joint. So these are just a representation. We will be needing these representations, and actually speaking these are more of bookish symbols. We will be using few more symbols which are actually used in the industries. So we'll discuss those things when we'll discuss the kinematic diagrams. So initially, to do the kinematics analysis, we need to draw the kinematic diagram of the robots. So when we'll be doing that, we'll learn more about these symbols.